So the rational function I'm going to use, all rational functions are in the form of f of x, and then that's equal to p of x divided by q of x, where p of x is the function that's in the numerator and q of x is the function that's in the denominator. And the reason why it's called a rational function because it forms a ratio or a fraction. I'm going to use this example here. I have x squared minus 1 over x squared minus 3x minus 4. The first thing you want to do is factor these. Here are the top factors into x plus 1 and x minus 1. The bottom factors into x plus 1 and x minus 4. What we can see immediately is that in our numerator and our denominator we have the same factor. So those are kind of cancel out, sort of. What we have here is something called a removable discontinuity. And what that means is that we're going to be able to take out this factor that we have here from our consideration when we actually look at what the graph's going to look like and how it's going to behave. But we have to make sure that this number here, where x is equal to minus 1, is not going to be in our domain. So when we graph this, we're going to get something that has a line, and we're going to get a hole in our graph. And that's what it's going to look like at x is equal to minus 1. Okay? You with me on that? All right, so first thing we want to do is we're going to set our numerator equal to 0. And that's going to find any zeros that we have or our x-intercepts. So I'm going to set x minus 1 is equal to 0, and I'm going to get x is equal to 1. So I'm going to have an x-intercept where x is equal to 1. The next thing I'm going to do is I'm going to set my denominator equal to 0. That's going to be x minus 4 is equal to 0, or x is equal to 4. This is going to tell me of any vertical asymptotes that I have, because these are numbers that are not in my domain. And as you get really close to this number, the graph is going to go to positive infinity or negative infinity. Next thing I want to do is figure out where it crosses the y-axis. And to do that, I set the function equal to 0. Because when x is equal to 0, that's where the function exists on the y-axis. So I'm going to evaluate f of 0. That's going to be 0 squared over 1 minus 1. And then 0 squared minus 3 times 0 minus 4. So that's going to equal to 1/4. So that's going to be my y-intercept is going to be at the coordinate point 0, 1/4. And then finally, I'm going to look at my end behavior. And I have a video on this specifically, so I'm not going to beleaguer the point. But I will just kind of review and say, look, if you're going to have the degree of your polynomial is on top is greater than the degree of your polynomial on the bottom, your graph is going to either go to positive infinity and negative infinity. If you think about it, if we have, for example, let's say I had x cubed over x squared, and then this would be as x goes to infinity. This cube part here is going to be way bigger than this part here. So it's going to be infinity cubed or infinity squared. So it's going to go towards infinity. It's going to kick the butt out of this. Whereas if we had vice versa and I flipped over and I had x squared over x cubed, as x goes to infinity, this whole thing is going to go to 0. Regardless of what numbers you have. It doesn't matter if you have coefficients in front or whatever. Infinity cubed is going to crush infinity squared. And as we have numbers where the number on the denominator gets really, really big compared to the number on top, it's going to go to 0. Think of, this number, 1/10,000,000th. That's really, really close to 0. So as this number gets bigger, we go to a billionth, a trillionth, a quadrillionth, or infiniteth, whatever the hell that is. This is going to go to 0. Okay? Y'all with me on that? Now, in our example, the degrees are the same. So because of that, it balances out as we go to infinity. So this doesn't matter, this doesn't matter, this doesn't matter. The only thing that matters is the x squared part, and the degrees are the same. Now, if we had a number here, like 5, this would still be 5 times bigger than this. Well, 5 over infinity, 5 infinity divided by infinity is going to be 5. Sounds weird, but that's kind of where it's going to taper off to. It's going to approach that value of 5. So when you have degrees that are the same, the horizontal asymptote is the ratio of the leading coefficients. So it's going to be this value of 1 over 1 here. And so the end behavior is going to be y is equal to 1. So now I can take a look at what this graph is going to be looking like. I got a y-intercept at 1/4. I got an x-intercept at 1. I've got a vertical asymptote at x equals 4. And then I've got a horizontal asymptote at x equals 1. So it goes through the graph here, and it goes through the graph here. Now, as it approaches this vertical asymptote, it's either going to go to positive infinity or negative infinity. So we have to decide, where is our graph going to go? Well, if it's going to go through these dots, it's going to come and approach this vertical asymptote on the negative side, and then it's going to approach the horizontal asymptote on that side. So it's got to look, oh, that's terrible. Nope, I'm still erasing. Sorry about that. Remember that we also have a hole in our graph when x is equal to -1. And that's our removable discontinuity that we had up here. And then we're going to have this line that goes like this. Now we have to figure out what happens on the other side over here. Is it going to be over here, or is it going to be over here? Well, it's going to be at the top. And the reason why we know it's going to be at the top is because we don't have a 0 here, right? So there's no place for the graph to cross the x-axis. So it has to be up here. Okay? Something like that. The reality is, I don't really care about the graph. What I care about for you guys is figuring out where the x and y intercepts are and where's the horizontal and vertical asymptotes. When it comes to actually graphing it, you're probably just going to use a graphing calculator anyway, like GeoGebra. Here, I've graphed the function using GeoGebra, and we can see that we have our horizontal asymptote, we've got our vertical asymptote at 4, we've got our 2 points of contact of our x-intercept and our y-intercept. The only thing that this graph is not going to show us is our removable discontinuity. No matter how much we zoom in on -1, we're not going to find that hole. It's not going to show us what it is. And the reason is because it's infinitesimally small, meaning that this really doesn't, I don't know, I don't want to go into deep dark dive of infinitesimal, but it does exist. It's just so small we can't see it. Okay? When you do your homework, you're going to have to select which graph it's going to be. You're not actually going to have to graph them, I think, for the most part. Okay? It's been a while since I've looked at your homework, but I think for the most part, you're just going to select which graph it's going to be. Capiche?